Alright, in the last video we talked about what an infinite series was, how to determine whether the infinite series is convergent or divergent in terms of the sequence of partial sums for the series. And then we also introduced geometric series in particular and looked at how to determine whether the geometric series, a given geometric series, is convergent or divergent. If it's convergent, what its sum is. And then we looked briefly at a so-called telescoping series. Now I want to look at an important convergence theorem. And it says that if a series is convergent, then the terms that we're adding, the limit of that sequence must be 0. And that's what we kind of talked about when we first, in the last video, when we talked about the number 1/3, right? We had an infinite number of things adding up. And we said, well, in order for that thing to converge, those things we're adding up have got to get diminished, have to go to 0, have to get smaller and smaller. Otherwise, there's no chance for the series, the infinite series, to be finite. So this makes sense, and let's just prove that. So first of all, if I let S be the sum of the convergent series, right, then what are we saying? The limit as n goes to infinity of the sequence of partial sums is that sum. Right? That's the definition of when an infinite series is convergent. Its sequence of partial sums is a convergent sequence, right? And the limit of that sequence, S, is the sum of the series. So what is the nth term of the sequence of partial sums? It's just, remember, the sum of the first n terms that we're adding up in the sequence. Remember, there's two sequences we're talking about, right? The sequence of terms in the series itself, the a sub n's, and then this sequence of partial sums. Now, if I were to have looked at the previous term in the sequence of partial sums, this is the nth term. The previous term would be s sub n minus 1. That's going to be a sub 1 plus a sub 2 plus a sub 3 all the way to a sub n minus 1, right? And I'll have you note that if I take s sub n and subtract this, right, take this minus this, notice when I subtract, the a1's cancel, a2's, a3's, all the way down, and there'll be an a to n minus 1 right before this a sub n. It will cancel with that one, and we're just left with what? A sub n. This should make sense, right? Because to get to the next term in the sequence of partial sums, I'm just adding the next term in the sequence that I'm adding up, the a sub n's. Okay? So now, when I take a look at this expression, and I say, what's the limit as n goes to infinity of this? What's the limit? If both of these are equal, what's the limit as n goes to infinity? That limit has to be equal. And notice here, the limit as n goes to infinity of s sub n minus s sub n minus 1. Well, really that's just the limit as n goes to infinity of s sub n minus the limit as n goes to infinity of s sub n minus 1. All right? So we're splitting up that side. And both of these limits exist because we're saying this one right here is s, right? This is s, right? What about this one? Well, if n's going to infinity, sn's going to infinity, where's s sub n minus 1 going to, right? The n's still going to infinity, so this subscript still, this index is still going to infinity. It's the same thing as this. It's still going to s. It doesn't matter where we start in the process with the sequence, right? Remember, we talked about that. I can eliminate the first 10 terms in the sequence, and the limit is unchanged. I can eliminate the first 100 terms in the sequence, and the limit is unchanged. What we're approaching is n goes to infinity, right? And so we can see now then what happens. S minus s is indeed 0. And that's a proof, if you will, of why the limit of the terms has to be 0. We kind of knew it intuitively, and so that's important. Okay. Does that mean every time the terms that we're adding up go to 0, then the series converges? No, it does not, right? If the limit as n goes to infinity of the terms we're adding up goes to 0, then this series may or may not converge. Okay, and we're going to give you an example of a series where that happens here in a minute. Okay. Now the contrapositive, what in the world's that? Well, it's this. If this theorem is true, right, if the series converges if the limit is equal to 0, then if the limit as n goes to infinity of the a sub n is not 0, then this has to diverge, right? And just think about it. You know, we were talking about that when I was adding up the terms in the series for 1/3, the things we were adding up were getting smaller and smaller. But if they don't get smaller and smaller, if they approach something like 1, then we're just adding way out there at n equals infinity. We keep adding 1. If you keep adding 1 to something forever and ever, that's not going to converge. That's going to just get bigger and bigger and bigger, right? And so this is what we call the nth term test for divergence. And if the limit of the terms we're adding up the limit of that sequence is not 0, okay? And that can mean, you know, the limit is any real number, not just infinite. It could be infinity, certainly, but it could just be the limit as n goes to infinity, a sub n is 4, you know, then this series diverges. All right, let's take a look at a couple examples. Here's the terms we're adding up, cosine of 1 over n. So what I'm going to look at is I'm going to say, what's the limit as n goes to infinity of cosine of 1 over n? What's the limit of the terms that we're adding up? Well, remember, when I'm taking the limit of a composition, I can push the limit inside, provided the function cosine here is continuous, and it is on its domain. It's continuous everywhere, so I can take in the limit as n goes to infinity, 1 over n here. And what is this limit here? What's the limit as n goes to infinity of 1 over n? Well, that's easy. That's going to 0, right? So this limit as n goes to infinity of cosine of 1 over n is approaching cosine of 0, which is equal to what? Cosine of 0 is 1. Okay. But 1 is not 0, right? Because if the limit of the sequence of terms we're adding up, the a sub n's, is not 0, which is in this case, then the series diverges. So I know that the series diverges. Let's look at this one. This is more complicated, right? Again, n equals 1, you know, going to infinity, does this series converge or diverge? Again, I'm going to take a look at the limit as n goes to infinity of n squared minus 5 over 3n squared plus 4n plus 2. Now, most of you know already the value of this limit. As n goes to infinity, of course, you have an indeterminate form, infinity over infinity. Both of these are going to infinity. But I could apply L'Hopital's rule, for instance, right, since this form is infinity over infinity. And I get the limit as n goes to infinity. 2n is the derivative of n squared minus 5. And over here I get 6n plus 4. I'm still infinity over infinity. But I can use L'Hopital's rule one more time. And the derivative of the top is 2. The derivative of the bottom is 6. And what's the limit of n goes to infinity of 2, 6? 2, 6 is just a constant. It's 2, 6, which is just 1/3. Okay. Now some of you can go right to that. You remember the idea of the fact that we have the degree in the numerator and denominator is the same, that this limit is going to be equal to the ratio basically of those two dominant terms. It becomes 1/3. But at any rate, we need to understand how to find these limits. But again, 1/3 is not equal to 0. It's closer to 0 than 1, but it's still not equal to 0. And so the series again diverges. That's what we conclude by the nth term test. And you're going to see me start doing this a lot when I say something converges or diverges by a particular test, because we're going to learn some different tests. And this is, one of our first tests that we're learning. All right, one more example. The a sub n's here are real simple now, just 1 over n, which, hey, I know that's in my sleep, right? The limit as n goes to infinity of 1 over n is 0. So the terms are going to 0. Does that mean this series converges? No. This really tells us nothing. The series may diverge or converge. We don't know. So it's real important. Just because the terms go to 0 that we're adding up doesn't mean the series is going to converge. Okay, that's a very common mistake. Right? In fact, it turns out that this series here is divergent. This series is divergent. And I'm going to prove that to you later on, not in this video or the next, but later on. This series is real important, and we give it a name. It's called the harmonic series. It's called the harmonic series. And so this series is divergent. As I said, we'll prove this later. Okay. Now, when we're talking about convergent series in determining their sum, we can use the following properties for convergent series. If we have this series converges to capital A, this series converges to capital B, and C is any real number, then the infinite series of C times A sub n, I can pull the C out and then find the sum of the series, which we said was A. So the infinite sum of a constant multiple is the constant times the infinite sum, if it's convergent. Same with adding, right? The infinite sums, right? The infinite sum of a sum of an infinite sum, if you will, sum of infinite sums is equal to the individual sums of those two infinite series. And so let me illustrate how these properties would work here. What's the sum of this infinite series? Well, I don't even know, is it convergent? So we're going to see whether it's convergent after we do a little manipulation here. So first of all, I'm going to write this as I'm going to break this up into two fractions. Right, I can do that, right? I can break this up into two fractions, right? And now I have, from this thing, right, I can split this up into two infinite series. I'm just going to write this as 4/5 to the n. Do you see that? 4 to the n divided by 5 to the n is 4/5 to the n. So I can write it that way, two sums. And then this 6 is a constant multiple. I can pull it out. And I'm left with 1 over 5 to the n, which is the same as 1/5 to the n, since 1 to any power is 1, right? This would be the same as 1 over 5 to the n. Okay. Now I can do all this provided the series I end up with are convergent. Are these two series convergent? They are. This is geometric. It's a geometric series, right, that we talked about last time. Notice the first term when n is 0 is just 1. The next term is going to be what? 1/5, and then 1/5 squared, and then 1/5 cubed, and so on. So it's geometric with a equal to 1 and r equal to 1/5. Since r is less than 1 in absolute value, we know that the sum here, so for this part, the sum here will be what? Remember, it's a, which is 1 over 1 minus r. So that's where we're getting this from. Remember the formula for geometric series, the sum was equal to that. Okay, plus, right, don't forget we got plus. What's this? This is also geometric, right, with a equal, again, 1. When n is 0, I get 1, and r equal to 4/5. And so, since r is less than 1 in absolute value, this is convergent. Okay. Now, I'll let you do the arithmetic on this. You get 1 divided by 4/5 here, 1 divided by 1/5 here, multiply that by 6, add them together. I'll let you finish that out and show that this is 25 halves, or 12.5. Okay, so I can make use of those properties provided I get to series that are geometric and, of course, series that I can find the sum for. So they got to be convergent, rather, and we've got to be able to find the sum. Okay, so there is an example of that. Now, you'll find that helpful in some of the homework problems, doing things like that. I just want to close this video with a little application. I haven't had much application, and this one's very contrived, but it's kind of interesting. So a ball with perfectly elastic bounces. So this is obviously not realistic in terms of what real happens, but let's just suppose it's going to be dropped from a height of 6 feet, and it begins to bounce. The height of each bounce is 3/4 of the height of the previous bounce. What's the total vertical distance traveled by the ball? So I'm going to kind of draw a little picture here of what's maybe happening. So initially we're going to release the ball from a height of 6 feet. So let's let this be 6 feet. Right? And I'm going to take that ball and drop it, and it's going to hit the ground. Bing, and it's going to bounce up 3/4 of the original height and then come back down. Right? And then it's going to bounce again 3/4 and come back down. And then it's going to bounce again 3/4 of the previous height and come back down, right? And so on. That's going to continue forever. Now, this height is 6. What's this height here? What's this height going to be from here to here? Well, it bounces back 3/4. It's 3/4 of the original height, which is 3/4 of 6 feet. All right. What's this height going to be? Well, it's 3/4 of the previous height. What was the previous height? 3/4 of 6, which is 3/4 times 3/4, or what? 3/4 squared times 6. And you get that, and then the next height, what's the next height going to be? 3/4 cubed times 6. And the next height, 3/4 to the 4th times 6, and so on. And so what is the total distance the ball travels? Total vertical distance. I'm not counting, traveling horizontally, just up and down. Well, it's going to be equal to, well, initially we dropped 6 feet. Okay? But then we go up and drop down this height. So we got to double it, right? 2 times the 3/4 times 6. Right? There's that and that. And then 2 times 3/4 what? Squared times 6, right? For the next one. And then 2 times 3/4 cubed times 6. And forever and ever, right? It's perfectly elastic. It continues to bounce forever, never stops. There's infinite sum. Infinite sum here. But notice here I can do a little manipulation. This is what I'm going to do. I'm going to keep the 6 by itself. Everything after the first 6 term has a 2 and 6 factor, doesn't it? 2 and 6 factor. So I'm going to factor out 12. 2 times 6 is 12. And what am I left with? 3/4 here, plus what? 3/4 squared, plus what? 3/4 cubed, etc., etc., right? What do we have here? We have an infinite series, right? In fact, it's a convergent geometric series. Right? And our first value in this particular series, this is separate, right? But it's what? 3/4. And what's the value of r? R is also 3/4, right? I multiply by 3/4 to get the next term that I'm adding up. And so the sum, A over 1 minus R, is 3/4 divided by 1 minus 3/4, which is 3/4 divided by 1/4, which is 3. And so, what's our total vertical distance? 6 plus 12 times all of this infinite sum, which is 3. Right? That's 36 plus 6, 42 feet. So our perfectly elastic ball, which will bounce forever, right, is approaching a total up and down vertical distance of 42 feet. Okay, this is a mathematical thing. Obviously, no ball is perfectly elastic. It's going to have friction and slow it down, and eventually the bounces will die down. But this is kind of a neat application and helpful in other areas. Okay, not a whole lot of application in this section. The next video will talk a little bit more about the sequence of partial sums and just some understanding of the relationship between that and the infinite series.